All right, this chapter is going to be on entirely on right triangles. Okay, so we're starting a new chapter, chapter 9.1. If you would prefer to print off these notes, they're posted on PowerSchool in a link right above the video. Go ahead and print them out before you start this video. This is going to be a really important lecture to have the notes with you because it's going to be a lot of figures, and so unless you want to have to pause the video to draw the pictures every time, I would just go ahead and print them off. Okay. So we're going to define a couple of things this chapter pertaining to right triangles, and one of the things that we're going to define, and you can add this to your definition sheet if you still have it, is called an altitude. Okay, so I'm going to read you the definition and then I'm going to show you what it is. An altitude of a triangle is a line segment through a vertex that is perpendicular to, i.e. forming a right angle with, a line containing the base or the side opposite the vertex. So this is the technical definition, and in the parentheses I kind of put what I thought made a little bit more sense. So I'm going to just take out all the stuff that maybe doesn't make sense and just make it a little bit simpler. So if I were putting the simplest version of this definition, I would put it like this. An altitude of a triangle is a line segment through a vertex and perpendicular to the opposite side of the vertex. So here we have a right triangle. Okay. And I forgot to take this out. And if I were to draw an altitude in this triangle, I would need to draw it through a vertex. So I'm going to pick this vertex C and draw a line that's perpendicular to the side opposite that vertex. So I have a line here that goes through this vertex and goes straight to the opposite side so that it forms a right angle. And there's actually only one altitude that I could draw that would go perfectly perpendicular to the opposite side. I couldn't draw another line through this vertex like this that would be perpendicular. You can see right away that would not be perpendicular. So this altitude, even though it's not necessarily the best drawn, is actually the only altitude in this triangle that I could draw that would be perpendicular to the opposite side like that. Okay, so there's only one altitude coming from each vertex. So that's an altitude of a triangle. Why are we learning about an altitude? Well, because the altitude actually helps us a ton. There are lots of things we can know about this triangle. For example, Theorem 9.1 says this: if the altitude is drawn to the hypotenuse of a right triangle. So, in other words, if we're drawing the altitude that's going to intersect with the hypotenuse, which if you remember, the hypotenuse of a right triangle is the longest side of a right triangle, and the two other sides are called legs. So here in this triangle, this would be the hypotenuse down here. I'm just going to write HYP because it's the longest side, and this would be a leg. And this would be a leg. Okay? So, if an altitude is drawn to the hypotenuse of a right triangle, then the two triangles that are formed are similar to the original triangle and to each other. Here's what it's saying: that because I drew this altitude, there are now two triangles that are formed. Here's a new triangle right there. And here's another triangle right there. And what this theorem, Theorem 9.1, says is that if the altitude is drawn, then triangle ABC, our original one, is similar to triangle, let's see, ABC is similar to triangle ACD, which is also similar to triangle CBD. And if you remember, there are two things that we know about triangles that are similar The first being that their corresponding angles are congruent, and 2, the corresponding sides are proportional. Okay? The corresponding angles are congruent and the corresponding sides are proportional. But that's not all we can know. There's more. Theorem 9.2 says this: if the altitude is drawn to the hypotenuse of a right triangle, so the exact same scenario we had in the last theorem, then the length of the altitude is the geometric mean of the lengths of the two parts of the original hypotenuse. Here is what this is saying, that this length CD, that's the altitude, is the geometric mean of the lengths of the two parts of the original hypotenuse. Well, you see how AB is the original hypotenuse. So the two parts that this altitude forms are AD and DB. So what this theorem is saying is that remember, a geometric mean is some number x such that it goes here in the proportion and then the two values go there. So here we'd have two proportions that we'd be setting equal to each other, and the length of the altitude, which is CD, would go here and here, and that would be the geometric mean of the two parts of our original hypotenuse, like that. So this would set up a proportion like this that would help us solve for lengths of this triangle. But that's not all we can know. Theorem 9.3 says if the altitude is drawn to the hypotenuse of a right triangle, so the exact same scenario, then the length of each leg is the geometric mean of the hypotenuse and the part of the hypotenuse touching the leg. Now this one's really confusing, so I'm going to try my best. Remember, in the original triangle, this is a leg, and this is a leg, and this is our hypotenuse. Okay, so don't forget that. Keep that in mind. What this theorem is saying is that the length of each of these legs, this leg and that leg, is the geometric mean. So I have those legs, so one leg being AC is the geometric mean of, which means that I'm going to be setting a proportion that's going to look like this. I'm going to do this for both legs because this is true for both legs. So the length of each leg is the geometric mean. So we have AC here, so here's the length of this leg here. So that's CB, and CB is the geometric mean of the hypotenuse. So the entire hypotenuse is one part of this proportion. All of this, AB. Okay? It's the geometric mean of the hypotenuse and the part of the hypotenuse that's touching the leg. So if you just remember from our last slide, we are now splitting the original hypotenuse into two parts, AD and DB. So the part, whichever part of the hypotenuse is touching the leg that we're talking about, that's going to be the other part of this proportion. So for AC, what part of the leg is touching AC? Well, clearly it is AD. Okay? And for CB, what part of CB is touching, what part of the hypotenuse is touching the leg? Well, clearly that's BD. So the length of each leg, AC and CB, is going to be the geometric mean of the entire hypotenuse and the part of the hypotenuse that's touching the leg. Now what we're going to do is we're going to do 3 practice problems that are going to use, we're going to do a few practice problems that are going to use each of these theorems. Okay, so we're going to go one by one. So here's a practice problem right here, and this is going to use theorem 9.1. Or no, I'm sorry, this is going to actually use theorem 9.2. Which says this. If you remember, theorem 9.2 says that the length of the altitude is the geometric mean of the two parts of the original hypotenuse. Okay, so here we would set this up like this. We have a proportion. The length of the altitude we know is x, so we put that here and here in our proportion. And the two parts of the original, the whole hypotenuse would be 9, 6 plus 3, so the two parts of our original hypotenuse are 6 and 3. And then we need to cross multiply to solve this. So we'd have x squared equals 18. So when I take the square root of both sides, in order to get x by itself, I need to take the square root of both sides. And x equals root 18, which simplifies to 3 root 2 if I simplify that. Okay, let's try another. All right, here we have to kind of figure out, okay, what theorem are we going to use? This one's going to be theorem 9.3, which remember said this, that the leg of our original triangle, x, is going to be the geometric mean, so it goes here and here in our proportion again, of the original hypotenuse. Now look, we already said the length of our original hypotenuse here is 9, and the part of the hypotenuse that's touching the leg. What's the length of the part of the hypotenuse that's touching x? Well, it's 3. So this is going to be 3. When we cross multiply, we get that x squared is 27. And so x would equal root 27, which simplifies when I simplify this to 3 radical 3. Okay, let's look at a couple more. How would we do this one? I'm going to go ahead and tell you. This one's going to be theorem 9.2. How would we do this one? I'm going to go ahead and tell you. This one would be theorem 9.3. How would we do this one? This is for honors, and this was going to be 2 steps. And we're going to have to actually use theorem 9.1 first, and then use theorem 9.3. And this one as well will be just straight up theorem 9.2. So I actually want you to try each of these. And your practice problems will be twofold. Your practice problems will be, if you're not in honors, doing these two on your own based off of what we did here. And if you are in honors, you need to do these two and these two, as well as the practice problems that I've listed on PowerSchool. Okay, so that is your lesson on 9.1. Do all of the problems in the notes, and then do the practice problems that are listed on PowerSchool as well. Thank you.